So today we are going to discuss about the timer and the count delay, uh, how the microprocessor is going to execute an instruction, how much time it will require to execute a program. This all will be done in this, as well as per the requirement, if we are in requirement of delay and how the program can be done to, to make a program delayed. The actual requirement is to write a program as small as possible, having less number of instructions, so that whenever a program is executed, it should take less time. Meaning thereby the program written in such a manner that it should have minimum number of line and it should take minimum number of time to execute for the effective use of the processor. But there are many applications in which we are in requirement of providing a delay, and this delay can be provided with the help of writing a program. Some instructions are used uh, to provide the delay within the program so that the delay can be achieved. Now there are many applications. There are applications such as process control. There are applications such as traffic signal, and other applications also in which we are in requirement of delay. So that's why it's important to discuss timer and the control delay. Now, as you have seen that there are many programs in which we used to do the looping process, meaning thereby looping is a kind of a technique in which certain instructions are being repeated many times. And for applying the looping process, we are in requirement of using counters. So counters will be playing a very important role along with the looping to provide the delay. Now, as per the requirement, we can use counters as up counter and the down counter. Up counter is a kind of a counter in which we are going to increase the value of the counter, which is initialized. And in another, we are using the down counter in which we are going to decrease the count value. Now, the important part of the programming is there are three aspects. One is how to start, then how to proceed further, means what are the processing part, and third one is how to exit. Now, the starting part of the program is important because before writing the program, before you start the main execution, you must initialize certain things such as memory pointer or the counter. Then the second important part is what kind of application for the solution of what kind of problem you are trying to find out the solution, and for that you will be writing instructions. And the third is how to exit from the program. So there are many ways how to exit the program: by checking the counter or by reaching to a decision to end the program. So for that particular purpose, counters will be used. Now, the time delay can be done by loading a particular register by a certain count value, and that count value can be set to be the delay count. And then we are setting a loop, and after setting the loop, we will be decrementing the counter, and loop is executed many times. So as many times the loops are executed unnecessarily, it will be consuming certain time till the count value becomes 0. Now, how to estimate the time whenever you are executing a program? We know that each instruction which is being executed by the microprocessor, it requires certain time. And this time is measured in terms of instruction cycle. Instruction cycle is the cycle, the total time required to execute one instruction. And it consists of many machine cycle. And machine cycle is the cycle which is estimated that number of times the microprocessor is going to fetch the memory or the input output devices are known as machine cycle, which is made up of 3 to 6 T states. And T state is nothing but it's a one subdivision of the operation which is being performed by the processor at a particular time. And you have seen while discussing the timing diagram, you have seen that if it was a opcode fetch operation, it used to take 4 T states. But if it is a memory read operation, it used to take the 3 T states. So 3 T state is the time which is required to execute the instruction. Now, how to estimate the value of the T state? It depends upon the crystal frequency which is attached with the microprocessor. And this frequency of the crystal is going to give the time period. And this time period is estimated as a 1 T state or 1 clock period. So as it depends, the clock period depends upon the frequency of the crystal which is connected with the microprocessor. So if the operating frequency, now there are two kinds of frequencies which are associated with the crystal. One is crystal frequency and another is operating frequency. And operating frequency is always half of the crystal frequency. Suppose the crystal frequency is 5 megahertz, then the operating frequency will be 2.5 megahertz. And the clock period will be 1 upon 2.5 megahertz, that will be equal to 0.4 microsecond. So how this counter will be used to apply to implement the delay service? We know the property of the counter. We initialize the counter, we update the counter, and then we check whether this is the final count value. And if it is not the final count value, we go back and update. And this process is going on until the count becomes final. And when it becomes final, then it comes out. So if we want to create a delay, we have certain program before the update and the final count. We have certain program after that. And if we want to create a delay, because this particular moment, this particular set of the instructions which we use to update and check the final count value is going to create a delay. So now this delay can be achieved by two ways. One is to obtain the delay with the help of no operation instruction, NOP instruction. That is called the time delay using the no operation instruction. So whenever we put in between two instructions, whenever we put NOP instruction stands for no operation. And this instruction does nothing, but it consumes 4 T states of the processor time to execute. So by executing this no operation instruction, we are able to get a delay of 4 T state. So if we want a delay of 24 T state, so we can use 6 times the no operation instruction to be written in between the different instructions. Now how we are going to measure the value of the T state. 1 T state is equal to 1 upon the operating frequency of the processor. If the operating frequency is 2 megahertz, then time required for 1 T state will be 1 by 2 megahertz, that will be 0.5 microsecond. So if though no operation is consuming 4 T state, so it means 4 into 5, that will be consuming 2 microseconds. So one NOP instruction will be consuming 2 microseconds for execution purpose, and it does nothing. So it is creating a delay of 2 microseconds while executing your program. It depends upon the operating frequency. If the operating frequency is 2.5 megahertz, then it will be 0.4. Then in 4T state, will be taking 1.6 microseconds. So it depends. So this is one of the way by which you can create a delay by using no operation instruction. The second way by which we can create a delay is to use a counter. Now we can use the counter, 8-bit counter, we can use 16-bit counter, depending upon the delay, how much delay we require. Now, one of the application of the delay is the traffic light signal, in which there are 4 ways through which the traffic has to be passed. And at a time, the junction will be allowing only one side to move ahead. And the rest of the side has to wait for a certain minutes of the time. It means before it is going to become green signal, after the red signal, there are in requirement of providing certain delay, so that after 2 minutes of the time, the red signal will become the green signal. So this is very good example of the delay application while writing the program for the traffic signal control. So time delay using the 8-bit counter, the flow chart of that is here, in which we will be using one register, and that register will be loaded with the counter value. We decrement the counter and we check the counter whether it has become 0 or not. If it has not become 0, it will go ahead. It will again decrement the counter. It will check the counter, and this process will go on. So this process, if suppose we have taken the counter value as 10 and decremented, it will become 9. Then it will check. Then it will go back. It will become 8. Then it will go back. It will become 7. So the time will be consumed unnecessarily to create a delay in executing the program if this part is being used. So how we can do with the help of a program? It has been shown here. Suppose I am using a C register, and C register is used as a delay register, and we are putting some count value into the delay register C. I don't know what is the value of the count. It may be 0, 4, it may be 5, it may be 10, it may be whatever it may be. So the purpose of MVIC count is to load the count value into the C register. And since it is a 2-byte instruction, so it will be taking 70 states. If you remember the timing diagram, the opcode fetch operation used to take 4T state, and memory read operation used to take the 3T state. And in this instruction, MVIC count, we have both the operations. The first one is the opcode fetch, in which the code of MVI will be fetched. And second one is the memory read operation, in which the count value will be read. So it will be taking 70 states. Then what we are doing, we are decrementing the counter, that is decrementing C, and it will be taking 4T state because it is an opcode fetch operation. And the third one is the jump on no zero loop. If count is not equal to 0, repeat. And it used to take 10T states oblique 70 states. 10T state it used to take whenever the condition is satisfied. Means whenever it is jumping back, it will be taking 10T states. But when the count value will become 0, it will not go back, it will come out. So at that time, it will be taking 70 states. So that is why it is written as 10 oblique 70 states. 10T states while it is going back to the loop, and 70 state whenever it is exiting from the loop. It means if the count value, whatever is, up to count -1, it will be taking 10T states. But when the count value will become 0, it will be taking 70 states. So depending upon that, we have to consider that how many T states will be consumed in executing this particular program. And then we will be able to calculate the time, because we know the time period of 1T state multiplied by the total number of T states which are available. Now, If you try to count, there are 70 states in the first, 4 T state in the second, and third instruction is taking 10 T states. So if the count value is 5, so it will be decremented, it will become 4, and it will jump again. So once 70 state will be consumed, but 4 plus 10 will be consumed at least 4 times up to count minus 1. And then later on, the 4 plus 7, it will be 11 T states will be consumed. So how to calculate this value? So total T state required to execute the given this above program is T out and the T loop. Whatever are the T states in the loop, loop is this one, and this is out of the loop. So that is why 7 T states. So we have divided total T state outside the loop and T state within the loop. So T out plus T loop will be the total T states. So T out, we know that it is a 7, so I will be writing 7. Then T loop, it will be taking 4 plus 10 T states for first, 4 plus T for the second, 4 plus T for the third, 4 plus 10 for the fourth. It depends up to count minus 1. So that is why T loop will be equal to count minus 1 into 4 plus 10, because it is 4 and it is consuming 10. So when this instruction is executed, it will consume 4 T state. When this instruction is executed, it will consume 10 T state. And this process is repeated until count minus 1. When it will become the count value, it will be having the T state as 4 plus 7. That is why it is written. So this 7 is representing MVIC. This count minus 1 into 4 plus 10 is consuming it is making the loop. And whenever it is coming out of the loop, it will be taking only 4 plus 7 T state, the last loop. Now suppose the count value is 5. So if the count value is 5, then total number of the T states will be 7 plus 5 minus 1 into 14 plus 11. It means total number of the T states which are used for executing this program will be 74 Ts. If the operating frequency of this particular microprocessor in which this program is being run is 2 megahertz, it means 1 T state is equal to 0.5 microsecond. So the total time required to execute the given program will be 74 into 0.5, because 74 is the total number of T states, and 1 T state is counting 0.5 microsecond. So 74 into 5 microsecond will be equal to 37 microseconds. So 37 microseconds will be consumed in executing this particular program if the microprocessor is working on the 2 megahertz operating frequency. So the question comes, now it depends upon the count value. If the count value is 10, though it will change 5 by 10. If the count value is 16, we will change 5 by 16 and so on. And so as the count value is going to increase, it is going to increase the execution time, because more number of time the loop has to be executed. So what will be the maximum delay which we can find out? So maximum delay can be found out with the value of the count, and the count value with the count value as maximum. Since this count value is an 8-bit number, and the maximum value which we can put in the count as a 8-bit number, we know that it is a FF, and this FF is equal to 255 decimal. So it means the maximum delay which we can obtain with this kind of program is by putting this count value as 255 minus 1 plus 14 into 11 into 0.5 microsecond, that is 1787 microsecond. And you can say that it is equal to 1.7 millisecond. So this is the maximum delay which is possible by putting a maximum count. Now the count value cannot exceed from 255 decimal, because the maximum value which we can put in this count is FF. Beyond that, we cannot go. So the maximum delay which is possible is 1787 microsecond or 1.7 millisecond. So what will happen if we want more delay? Instead of 1.7 millisecond or 1787 microsecond, if we want more delay, then what we can do? Then we have another process. That process is known as time delay using the counter, but the counter which will be used is a 16-bit number. How it works, the flowchart will remain same, but the program will be changed. Instead of loading the count value into a single register, what we do, we load the 16-bit register in a register pair. Suppose I am using BC pair to load the count value. So in this BC pair, I have loaded 2384, a 16-bit number as the count value. Then we are decrementing the count value. Then we are using two unnecessary instruction, move AC and then ORAB. The purpose of LXIB is to load the 16-bit count, that is 2384, into the BC pair register. And this instruction requires 10 T state. DCXB is going to decrement the BC pair register by 1, and it used to take 6 T states. Move AC is going to copy the content of C register into the accumulator and use take 4 T states. ORAP, it is going to do the OR operation with the content of B register with the content of accumulator. It is going to do the logical OR operation in between B and C. Of course, the value of C is loaded in accumulator and we are doing ORAB. So actually, physically, we are doing the OR operation with B and A, but logically, we are doing the OR operation with B and C. So it is also taking 4 T state. And again, the looping instruction, that is jump on no zero loop. If the result is not 0, it will repeat. And this repeat process, it will take 10/7 T states. So now let us find out that how many T states will be required to execute this instruction, and then we will calculate the time. So the total T state required will be out of the loop, T out plus T loop. This instruction is out of the loop, so it will be 10. And T loop will be count minus 1 plus count minus 1 into 6 plus 4 plus 4 plus 10. Plus the last loop will be 6 plus 4 plus 4 plus 7. So the total value will be equal to 10 plus count minus 1 into 24 plus 21. So if the count value is suppose 03FF, so 03FF, now one thing you have to be very careful that whenever we use the formula, in that formula, the count value is not written in hexadecimal. Always we have to convert the count value. Of course, whenever we feed the program, whenever we write the program and loading the count value into the counter, we will be using hexadecimal number. But while calculating the time required or T state, the count value should be converted into a hexadecimal. So if the count value is 03FFH, we have to convert this value into a decimal number. And then this decimal number will be put into this place in this formula. So this will be equal to 10 plus 10, 22 multiplied by 24 plus 21. This is 21. So that will be coming around 24559. These are the number of T states. And once you are able to know the number of T state, you multiply it with the time period, means the time required timing of 1 T state. So the total time required to execute this particular program, if the operating frequency is 2 megahertz, will be 24559 multiplied by 0.5 microsecond. So that will be coming around 12,279.5 microsecond, which is equal to 12.27 millisecond. Now, by using the 16-bit register and by using the 8-bit register, there is a difference. The 16-bit register will be giving 16-bit value, more large number of value, which has to be counted from top to bottom up to 0. So it means this will be executing the loop more and more time than instead of if we are using the count value in the 8-bit register. So that is why you are getting more delay. Now, the maximum delay which we can get in 16-bit register, the maximum value which we can feed is FFFF, that is equivalent to 65,535. This is the decimal equivalent of this hexadecimal value. So the maximum delay which we can find out is 0.8786 second. Means 0.8 second delay can be provided, maximum delay can be provided with the help of 16-bit count if the operating frequency is 2 megahertz. Now, so you see in 8-bit we are getting a 1.7 microsecond delay, 1700 microsecond delay. But in the case of 16-bit counter, we are getting 12.27 millisecond delay, and the maximum value which we can get is 0.8 second delay. So this delay is more than the previous one. But if your application requires more delay, besides using the single count value in the 8-bit register or by using 16-bit count value in a 16-bit register, we can also go for more delay. We can go for the nested loop techniques. Now, nested loop technique is different, and nesting of the loop or nested loop is known as loop within the loop. So it is going to create more and more delay. How it will be done? With the help of nested loop. Now, the nested loop means loop within a loop. The innermost loop will be same as I have explained, and the outer loop is going to set the multiple count to the delay provided by the innermost loop. So what does it actually means? When we were discussing about the ascending order program, we were using two counters, one counter and another counter. So one counter is working as a multiplier and another counter is working simply. So if there are 10 numbers which has to be sorted, required to be sorted. So what we do, we start with two counters. One will be loaded with 9, another will be loaded with 9. And the total number of the iteration which is possible in that particular case is 9 into 9, 90, 80. So that is why the outermost loop is called the multiple count, and the delay and the actual delay will be provided by the innermost loop. So let us see how this program can be written with the help of nested loop. Nested loop means we are using the two loops. So for that particular purpose, you have to use two delay count value, and for that you are in requirement of two registers. So first of register will be loaded with the multiplier count, and another register will be loaded with the delay count. And both these are similar type of instructions. So both will be taking 70 states. Then we are decrementing C, and jump on no zero, it is going back. So this loop is created over here. So, and once this decrement value will become 0, we will start decrementing the value of B. Until B is not 0, it will go start. So another loop is created over here. It means it is a loop within the loop. Now, the concept of the nested loop is such that the loop is called nested loop if the loop is not going to cross each other. If the loop is executing within itself, loop is within the loop is executing, that kind of loop is called nested loop. So the correct way of using the nested loop, that it should not cross each other. Now one loop is created by decrement of C and jump on no zero back. This is one loop. And another loop is MVI C and then MVI B, and we are decrementing. So this is one loop from first to fifth, and this is another loop from second, third to fourth. So this kind of loop is known as now jump on no zero back is again 10/70 state. Decrement B is going to take 40 state. Jump on no zero is again taking 10/70 states. So let us now calculate the value of total number of T state required to execute this particular program. Now T state required for the execution of the inner loop. Whenever we talk about the inner loop, the inner loop consists of MVIC, delay count, decrement C, and jump on no zero. This is the part of the inner. And out of that loop, this is outside the loop and this is inside the loop. So the total time which will be created, which will be exhausted, which will be taken by this three set of lines, MVIC, decrement C, jump on no zero, will be taking as 7 plus delay count minus 1 plus 4 plus 10, that is 14, plus 4 plus 7, last loop, that is 11. So this is how we are going to count the value of the inner loop. Now T state required for the execution of the whole program, how this whole program will be going to work. So that can be estimated as, we will start with 7 plus multiplier count minus 1, multiplier count minus 1, and these three is the T inner, plus 4 plus 10, that is 14. So this 3 constitute T inner, and this 4 and 10 is consisting of 14. So T inner plus 14. And the last loop will be taking 4 plus 7, that is 11. So 7 plus multiplier count minus 1 into T inner plus 14 plus 11. Now suppose the delay count is 65 hexadecimal, that is 101 decimal number, and multiplier count is 51, that is 81 decimal number. So by putting all these two values, first of all, we will calculate the T inner value. So T inner value will be 7 plus delay count minus 1 plus 14 plus 11. So delay count is 101. So we'll putting 101. So we are getting T inner value is 1418, 1418. And then by putting the value of T inner into the second equation, we will be getting 7 plus multiplier count is 81. So 81 minus 1 plus 1418 plus 14 plus 11 into 0.5 microsecond, considering that the operating frequency of the microprocessor is 2 megahertz. So it will be coming around 57 millisecond approximately. So you have seen that the delay count is going to increase if we are using 8-bit register, then 16-bit register, and then the nested loop. So nested loop is going to give more delay as per the requirement.